about quantum control with a specific focus on robust control, and then link that up to some reinforcement learning. Now, this is joint work with Ertaza Khalid. He is the PhD student on the project, done all the reinforcement learning work, really. We have Sophie and Edmund. They're sort of our theorists, mathematicians, control, theoretical physicists, and Carrie Whitener, she's sort of our experimental physicist involved. And yes, all the details of the work are available on this kyber.black website on this. You'll find all the papers and everything there if you're interested. But yeah, so control of quantum systems is really, well, generally said, making quantum systems dance to our tune. And really, in some sense, you're playing a tune to them with an RF signal or a laser. It's just amplitude modulation. So it's not really music that people would really like to listen to, I suspect. But generally, it is a way to try to steer their dynamics. Essential with that for quantum technologies to make these systems do something useful for us, whether that's computing, simulation, sensing, communication. It's an enabling technology for all of them. The specific part, of course, that we need is the robust control, so robust operation of the devices to fight all the noise, all the uncertainties that you have in the system. And you can bring it down to a certain level, but you can't completely get rid of it. There is error correction, but you can't get rid of error correction because no system is perfectly robust. But at the same time, if your system is not robust enough, error correction has a very high job to do. So it really works hand in hand with the two approaches. But specifically not what we're doing is not error correction itself. Now, most of quantum control, and you might have seen that before, is open loop control. So that means you'll have a model of your system, you run an optimization algorithm over that model to achieve your target by fiddling with the knobs, with the parameters. And then you'll hope that your system is achieving this. That's, of course, because of the measurement back action here, that you can't really just take a measurement and the system doesn't change. So that's really where the open loop comes from. But in particular, also, there's no explicit notion of robustness. So any kind of uncertainty in your system, how the controls behave to that, we don't know, at least in principle. There is another branch of control, sort of adaptive control, that would take measurements and then adjust their controls. Classically, easy, quantum, maybe not so easy. But there is a general problem with that when you say you'll take a measurement, see how the system is doing, and then adjust your control, because you can't simply be not necessarily in all cases fast enough to recover from a situation where your plane crashes, or for that matter, your quantum computer crashes, or whatever the alternative of that is. So it doesn't work as well as you might initially think on this. And so what we've been looking at is robust control that has some advantages over that because it uses direct feedback. Now, that's not specific to quantum systems. There are many standard classical examples of a feedback loop that actually doesn't require measurement. Even we could in principle. Classical example is the steam engine governor that works actually very robustly. You can see what the state of your system is, of course, compared to the quantum systems, but you don't have to. These systems are inherently robust. Maybe more modern example is an operational amplifier that really only becomes usable by putting these feedback loops in the circuits, that you don't get insane gains of your amplification, or also for other systems. So yeah, all of analog computing really works with operational amplifiers and these kind of feedback loops. That is the kind of direct or hidden feedback instead of explicitly considering measurement outputs and adjusting the control. So to make that a little bit more concrete, yeah, quantum control looks for optimal controls by maximizing the fidelity function. So we'll have here the standard Schrödinger equation on this, the time-dependent version of it, with your Hamiltonians, and we'll take the Hamiltonian apart here by saying we have a system Hamiltonian H0, that's the natural evolution of the system. We have 10 sort of dynamic controls, so control Hamiltonian specifying the action of your control on the system, effectively multiplied with an amplitude that can be time dependent. That's the standard control picture. What we've added is another H delta, which is a static control in terms of that we're effectively shaping the energy landscape, say, of a spin system. We do this a lot with spin systems here. So instead of sending in some RF pulse or laser pulse or anything along these lines, we're looking at just adjusting the local landscape of the systems, which turns into that kind of direct feedback later on. I put some more details in there of how this really works. Of course, yes, this system is solved with an exponential. Usually these are all piecewise constant controls or just a constant control if you have no time dependence at all. So these are just matrix exponentials to solve it. And then you're trying to maximize in general the fidelity, which very generically is essentially an inner product. But essentially you're comparing the state you get with the state you want. So for a state transfer, you take your initial state of the system, propagate it by the solution of your Schrödinger equation under the controls, and then compare it with your target state and see how close you are. And you maximize it. So you're 1 if you have the target state achieved, and lower than 1 down to 0 if it didn't work at all in terms of how far away you are from it. Instead of state transfer, you can also implement operators or quantum gates if you want, just by comparing the actual operator that you achieved with the system with your UT, your target operator on that end. Sorry, I think I went back. Yeah, no, there we go. On this, there are of course variations of these fidelities. In principle, anything that gives you sort of a bounded value, ideally between 0 and 1, but you don't even have to make it 0 and 1, that you can try to formulate these problems. And this also works to open systems. I'm just not covering this here to keep it simple on this, and open system make things a lot more complicated. At the same time, sometimes you can actually use the environment also to stabilize the system. You don't always have to fight the environment to get a stable part on this, but for this talk, we're not going further into this. That's the basic control problem. Now, in reality, and that's the problem of robustness, is this fidelity is a random variable because we have uncertain dynamics. No dynamics is ever perfectly 100% correct, even in quantum, particularly not experimental. And these uncertainties come from incomplete knowledge about the Hamiltonians, drift in these Hamiltonians over time, control field error, so the actual controls you're applying, how well can you shape the pulse that you're actually sending into the system? There are inevitably errors in there. There's initial state preparation errors, of course, as well. If you don't start precisely where you want to, you can end up somewhere else quite easily, actually. And then, of course, the general problem, decoherence, the interactions with the environment. Generally, what we started now fairly recently to try to quantify not just high fidelity, but also robustness is something we call a robustness in fidelity measure, very simply defined by a Wasserstein distance between the actual fidelity probability distribution that we get under all of these uncertainties with the ideal distribution, which is a delta function at 1. So if you look at that figure here, the green function, all your fidelities are perfectly at 1. That's what you want to achieve. In reality, you have some probability distribution here. The green and the blue line would be the cumulative distribution of them plotted here. They are not very good fidelities here. They really are very low, but that's just to illustrate on this. And the Wasserstein distance essentially compares or sees how much of the probability mass that is in your fidelity distribution do you have to move to the other distribution to make them equal. So sometimes also referred to as Earth movers distance. This is only the first order Wasserstein distance we are using for people who know. That's sufficient for our purposes on that. And with a delta function that effectively just becomes the integral over the cumulative probability distribution for the fidelity. Relatively easy to compute. It captures our high fidelity and the robustness, because the closer you are to the green, the more robust you are, the more tail you have, the larger this Wasserstein distance becomes, the worse it is. If you do it computationally in simulations, that means we need to run a lot of Monte Carlo simulations. You can also get it from experiments directly. Whatever gives you your fidelity measure can be put into that. The problem, of course, is when you see Monte Carlo simulations or corresponding many experiments, that it would actually be very expensive to optimize over. So it's not just a single function evaluation, it's many function evaluation with even more Monte Carlo simulations. But okay, I keep going back. Okay, but it overall serves very well as a post selector. Once you computed a bunch of controls, it gives you an idea how robust are they actually under your system uncertainties. And it really works for any fidelity measure. So that's a very generic measure that we can be using. If we now look more at a more specific problem, and then also more specifically what we do in sort of robust control, the specific problem here from where I have the results is a Heisenberg model of essentially a network of spins, spin 1/2s, or a network of qubits, if you want. You can think of that are coupled over the X, Y, and Z rotations. We can there's usually isotropic, so not kind of some anisotropic link in the rotations. We call this XX if it's only the XX and the YY rotation couplings. These are the extended Pauli matrix, and triple X if the Z is also isotropic in the coupling. And the JKL here, that's essentially tells us what is the coupling, usually only 0 or 1, so it's coupled or not. Mostly we're looking at chains and rings to keep it simple and somewhat realizable also on real systems. That's the natural evolution of the system. Our energy landscape term then become local Z rotations on each of the spins according to some local bias field delta K. That's our control here. So we only control the delta Ks, nothing else, no temporal dependencies. Makes the problem in some sense a lot simpler because it's lower dimensional. We make it even lower dimensional by saying we only want to transfer one spin from one part in the network to another network. So we look at the single excitation subspace for the Hamiltonian. Specifically, the examples I have in the talk are only the XX couplings. So that means our Hamiltonian is essentially the graph connectivity matrix with biases on the diagonal, a very simple structure, very regular structure. Now, what I should mention, though, is that with that system, this is not fully controllable in the sense that I cannot implement any arbitrary operation. I cannot do, in a quantum computing context, maybe implement any arbitrary gate on the system. That's just not possible because I have only a few controls. So already the dimensions with what I can do in general with the system and what I can implement with these controls do not match up. But we can do a state transfer. That's what we're specifically looking at. We also have examples where we can implement gates, but then if you have a C0 on 2 qubits, you need a larger network to get the degrees of freedom back to effectively implement a C0 on a subset of it. That is possible. The uncertainty then we represent with, well, structured perturbations, specifically here only to the Hamiltonian, again, to keep things simple. So we take the system Hamiltonian and add a delta S. The S is the structure of the perturbation. So that it's effectively a direction in which you're changing the Hamiltonian, and the delta is the strength of the perturbation. So how far are you going in that direction if you keep it simple? Generally, both can be uncertain. You can fix the structure and then say my delta is fixed, my delta has an uncertainty, or effectively both have an uncertainty. This gives us the fidelity distribution for the uncertainty, or how for describing the robustness of the system. And then, okay, we can compute the REM on this. But we can also do other things with it, which is more traditional in robust control. One is referred to as the log sensitivity. So that means we'll effectively just take the derivative of the fidelity with respect to our strength delta for a given S. So for a given structure, this is kind of infinitesimal robustness, what is happening at a particular point in your fidelity landscape, how quickly are you dropping down. If you do that for this kind of control system, what we're seeing, we're ending up with minimal fidelity. So these derivatives are actually vanishing at the optimal fidelity. Yeah, so if you have f equals 1, delta goes to 0, we call this super optimal. We'll get the derivative of the fidelity going to 0, not just in the directions of the controls, which you could say, okay, we are at a maximum in the control, but in all directions that we perturb the Hamiltonian that are beyond just the pure control part. So that's interesting, tells us this is very robust. This works by looking at the system as a linear time invariant system, the standard system that we're thinking about with robust control. And this is a bit of a trick. We're essentially just reinterpreting the Schrödinger equation. And from that, we can compute these things. And we actually interpret the H delta, our energy landscape control term, as a feedback term. So this is nothing else than the Schrödinger equation on the operator, not on the state. But that operator evolves according to the natural dynamics H0. And then we add this feedback term, a bit artificially, as a U of t, but that is just the H delta U effectively terms in. And that gives us mathematically, whether this exists in reality, we can ask a lot about it, but mathematically, this gives us a feedback loop into the system. And out of that loop, we can then effectively say, well, we can compute an error and the corresponding complementary sensitivity. Not going too deep into this, the error is essentially some operator on your output state. That's 1 divided by 1 plus L. L is the loop matrix that you'll get out of that system if you formulate it in that form. And we can show that this is about 1 minus F. So at super optimality, when F is 1, this goes to 0. The same with the sensitivity. This is L divided by 1 plus L, or effectively just the derivative of the fidelity in the derivative towards the delta. So at super optimality, that also goes to 0. The proof is in this paper down here. This is a lengthy, messy proof. But what we're seeing here, that we have optimal robustness in terms of the log sensitivity going to 0, at the optimal fidelity performance in terms of the error also going to 0. In classic robust control, that is not possible. There's a fundamental limitation that says this S plus T need to sum up to the identity. So you have an offset between your error and your sensitivity, which is the normal kind of behavior we're expecting in these systems. We don't see that. They both go to 0. So that gave us some confidence that this might actually be interesting for studying the robustness of these systems, on that because of this interpretation as a feedback loop. Now, we can take that further because the log sensitivity is what is happening effectively at the infinitesimal stage directly at your optimum or in your control landscape. We can, instead of that, again, formulate it as a hidden feedback law, this time in the Bloch formulation, because we need a real system. So that's known. I'll skip the details. This is messy and mathematical and technical and not much informative in that sense from what we're trying to do mainly. Yeah, but again, you have this time real natural evolution given by a matrix A and the feedback term U given effectively by C, which are our bias fields that we're applying to the spins locally. Then you take the difference between the perturbed and the unperturbed dynamics. So that Z being the R tilde, the perturbed with the delta S minus the R. You'll derive differential equation for that literally just by taking the difference. That's not much of a problem. But then you go over into frequency space because we don't want to work on that. Essentially, we don't want the infinitesimal behavior. We want essentially the larger scale behavior with this. In frequency space, so will you Laplace transform the whole thing, you end up with a Laplace transformed equation where this T operator for it looks like this. It comes from that expression. It's relatively straightforward. Important to notice, we put that in the Bloch formulation, and that means that matrix overall here is actually singular. So the inverse strictly does not exist. It is singular because we have an additional degree of freedom in the whole system, and that is we cannot observe the global phase. So that exactly gives us the extra degree of freedom. It is possible to invert that matrix by using a particular pseudo-inverse. This is not the standard Penrose pseudo-inverse. It's a different approach to that, but it works effectively similarly. And out of that, once we can invert that matrix over some technical terms on this, then effectively we get out of this essentially a bound on our T operator. So if our delta is smaller than 1 divided by mu, and that mu determines the bound, then our frequency operator, the noise operator in the frequency space is bound by mu. That's a short version of how structured singular value analysis or mu analysis is actually working. What we have to mention here that this is limited by linear dynamics, in particular by linear perturbations. That generally is not a good thing for quantum systems because you can very easily get a square root of gamma somewhere or things like this, and then you'll very quickly, that approach doesn't work that well anymore. But we can try to push it as much as possible. And again, what we're seeing in some example, this is for an 11 ring on this for a transfer. The red line here is this time the log of the probability of the transfer. So for the high, and we order them according to the probability. So for high performing controllers, our mu is okay. And as the probability drops, the mu, well, it descends actually quite a bit into chaos here. But we see exactly the same behavior, that the robustness drops as the probability drops, which again is something that doesn't actually, that contradicts that classical theory. We then looked at the statistics of that and said, well, we not just want to look at a lot of images, but see, is there actually a negative correlation between error and log sensitivity as you would classically expect or not? If you do that, it sometimes gets rejected at the sort of 95% probability interval. So we have cases where for the mu as well as for the log sensitivity, it gets rejected. It doesn't always get rejected. So some controllers might be robust. They're not all equally robust in that sense. And particularly what we're observing is some kind of idea of an emergence of classicality. So under decoherence, particularly, we see the classical behavior actually re-emerging. So again, we get the negative correlation between the error and the log sensitivity. And out of that, also what we're seeing, and I'm going through that relatively quickly, there's a lot more in the papers on this, that most robust quantum states are actually classical states. So all your nonlinear correlations go away, you converge to a steady state. That is a very robust state under decoherence. You don't move away from that, but you've lost all your quantum advantage. There are exceptions to that, of course, on this, if you think of decoherence-free subspaces and all of that. But largely, that's what our theory, or the classical robust control theory, is actually telling us. So there are clear limits to that classical control theory in terms of how far we can push it. And applying it to the quantum systems in a general sense becomes very difficult. But certainly, we have evidence for that particular energy landscape control scheme to be particularly robust. And that's interesting to actually build some better quantum devices, even we're looking at very low level individual gates or transfer here rather than anything else. So how do we find these robust controllers? And that's where the reinforcement learning now comes in all of that. And we are also getting back to that robustness and fidelity measure. Going back to the state transfer problem, starting from an initial state with energy landscape control, propagating the system, looking at the overlap with some target state, trying to maximize the overlap to transfer a single spin in a spin network. We have controls over the deltas, and we have control over the readout time as well. This makes it a fairly hard optimization problem, but it becomes even harder by actually adding the time to this, because trying to optimize across the time range, you have fairly deep ridges if you look at the landscape on that end. And we also here want to find robust and not just high fidelity controllers, but we don't really want to optimize over the rim. We could, but it would take a very long time, and this is already a hard problem. In addition to that, we'll have to assume, if we actually say, okay, at some stage we would want to run this on a real experiment and not just in simulation, we need to consider measurement noise, and we can only read out a 0 or a 1. We can only measure the state once. So we need to repeat that many times, but that means we need to estimate the fidelity from the 0-1 measurement. So we have binomial noise distributions for the fidelity as well. So that needs to be part of the model in terms of how we're simulating them. And then the uncertainties and the dynamics for now, we're limiting it to Hamiltonian uncertainties. If you look at the control landscape, and this is high-dimensional stuff, but we can do it in 3 dimensions with a 3-chain, make the biases symmetric. So they say the bias on the first spin is the same than the bias on the last spin, and the bias in between, we have an extra degree of freedom. So these are 2 control variables where we can plot things. We fix the time. I think this time was fixed to something like 6 for that chain. And for the 3-chain, this is actually analytically solvable. So this is not the most interesting problem, but it's the last case. For any longer chains, you can no longer analytically solve it. Without any noise. You see actually, well, not a too bad landscape in terms of that 2 ridges. This is the fidelity, so these yellow areas here, that's where you want to be on one. In between, you have this saw pattern, which doesn't look particularly good and makes the problem hard because you can get trapped here if you optimize sort of with the gradient optimization between that. Then if we add our perturbations in all directions, therefore each of the directions, so for all of the biases and the couplings between the spins. On this, we add a perturbation of some from a Gaussian distribution with some specific sigma of 0.03. You already see much of your structure goes away. This is one particular snapshot by just adding a particular level of noise to it. Uncertainty, I don't want to put on top of that. It would be very difficult to see, but your landscape becomes a lot more complex. Fairly difficult to optimize over with a standard sort of gradient-based optimization. If you go even higher to 0.87, you don't see many features anymore, and probably also not much of the robustness here is left. You have a few higher peaks left, and they kind of remain fairly high, but generally that landscape becomes very difficult to optimize. Before reinforcement learning, we use basic gradient-based optimization. That's a quasi-Newton LBFGS. With, importantly, many restarts. It actually works well to find high fidelity controllers without any noise in the system. Yeah, so we can find very high, this is the error here is 10 to the power -5. So very tiny errors on that one. The green line is the natural evolution, the blue line, the evolution under the particular controls. These are your control biases. Fourth, this is a 13, yes, this is a 13 ring, I think that we have in here. You see particularly also the symmetry of these biases, and that results from the symmetries that you've actually seen in the landscape. This is the best solution with the least error. This is the fastest solution, still with 0.999 fidelity at least. You get fairly high. Which one is more robust? Well, this one might be more robust. It's also the shorter time. You see the symmetries in principles with both of them, but you only get a few really high robust controllers or high robust short time controllers on this. And generally the other plot here shows in we fixed the time and ran LBFGS many times and just plotted the controllers and the fidelity, or here the error that we got. So this is the error we want to be low. You see there is something maybe just after 5, you find an actual 0 controller, but you find more controllers as you increase the time and the intervals become shorter, kind of Poincare recurrence if you want on this. The longer the time, the more controllers you find, but quite often your LBFGS optimization fails with absolutely horrible errors on this because you're somewhere in the landscape where you can't find any sensible peaks. Quite a lot of the landscape is flat where you see these saw patterns that make it very difficult. We do, in that case, of course, have a good analytical model. Yeah, that's sort of the perfect spin chain we're using on it. And we are not looking specifically for robust controllers. We have no idea how robust they are. We cannot easily handle noise and the fidelity if we were to try to optimize that over a real system. What people have done is effectively using Monte Carlo simulations or the equivalent coming from experiments, and then use LBFGS with finite difference gradients to try to approximate that. Of course, needs a lot more calls and evaluations to find the maxima, and it doesn't really work that well. And how robust these controllers are, we still don't know. There are alternative optimizers, sort of varying LBFGS for noise. We've tried a few, but we haven't had much success with them. So instead, we switched over to reinforcement learning. only giving you sort of the basic idea on this here. Essentially looking for an adaptive, completely model agnostic optimization. So this model still just uses a 2-layer network that what Etasa has implemented so far to learn the dynamics of the system. And we tried 3 different policy optimization strategies, common ones, DDPG, PPO, and TD3, just to see how they compare against each other and for that particular problem, in the hope that this will be able to handle the uncertainty in the fidelity and maybe improve robustness. And the robustness was a bit actually the surprise, because we found a lot more robust controllers. We'll see the results in a moment. So basically, you'll run the system with a fixed delta and t, initially a random guess. You read out many zeros and ones, or with a binomial distribution, to see how well did the transfer work by repeating the transfer a few times. At least if you were to do that experimentally in simulation, you can sort of shortcut a little bit. Out of that, you get an approximation for the fidelity. You feed that back in your optimizer. And at that stage, this can be an LBFGS optimizer, or this can be a reinforcement learning system. Just the reinforcement learning would have absolutely no idea about the dynamics. It would have a completely model agnostic system on that. Importantly here, because we do energy landscape control, and some people have used that for dynamic control. Yeah, but dynamic control, the policy you're learning can in principle be the control of the system. That you say, what at each state are you putting together? That this is not very realistic for an experiment, because usually these systems need to know, say, the full density operator of the system, but you can't really measure that. You can only get some information out of this, is one of the problems. But of course, you can use it in place of another optimization algorithm where you can compute this thing. But with the energy landscape control, we have no dynamic policy that we're running. So really what we are learning here is a policy that explores the control landscape. Our reward is the fidelity improvement. Our reward is simply just the fidelity, not even the improvement. The improvement didn't work as well as just fixing the fidelity. And the policy here is not the controller itself as in some other system, but essentially it aims to find the controller. In some sense, if you map that to a basic reinforcement learning problem, you're exploring a maze to find a heap of gold somewhere, and that's your maximum of the fidelity. But it is a continuous landscape. Yeah, so these are all continuous policy update strategies. So in some sense, we're looking for building a better LBFGS in that sense, but specific for a particular noisy problem. At some stage, maybe we can generalize it, but for now we haven't done that. So what are the results? Let's look first at the reinforcement learning and then compare it to LBFGS. So from reinforcement learning, first thing we've done is for an n chain from 3 to 10, fix the transfer from 1 to 3 here as one of the examples without noise. We see here repeated LBFGS runs the spread of environment calls that we need to find a good controller, which it has a model, it should be relatively low. If we do just random guessing instead, we end up with the green curve here, so that doesn't look so good, but it's purely random guessing what we can do. And if you look at the PPO here specifically, it lies somewhere between models and completely, I have no idea what I'm doing. So somehow this gives us some evidence, okay, we're learning something. It's not just random. Then we said, okay, let's compare TD3, PPO, and DDPG against each other, how well they're doing with noise. LBFGS wouldn't be able to run on this. If you have a noisy fidelity function, it just doesn't go anywhere. So LBFGS, we can only run without noise. What you'll see here, DDPG needs an awful lot of environmental calls. It performs okay if we look at the fidelity distributions that we're getting. This is kind of okay compared to the others. This hasn't been pushed to the limits that we really try to get 0.999 on this for some initial tests. Yeah, so it kind of does okay, but it is expensive. TD3 and PPO perform about the same. There is this peak. We haven't really been able to explain why this for the spin range 5, this is much lower. But generally, TD3 actually fails quite often, and we really can't get it to converge. So we settled for anything further for PPO, which actually seems to be doing an okay job. for the very straightforward, simple strategy. Now, how does a PPO perform with respect to the controller, to the robustness of the controllers that we find? Now, this is one example. We did a lot of these. There's a summary of this coming up, of a 5-chain for the transfer from the start to the middle. I should say from other work before, we know that from start to the middle, this is the hardest transfer for any of the spin chains, because the system will naturally never go to the center spin. From end to end, it will go eventually. It's a matter of time, and the time can be very long, so you can only speed up. But if you go from one end to the center, this is not the natural evolution that the system can actually perform, so you need control for it. And then if you look at this robustness and fidelity measure, which we would like to have at 0, so the lowest error closest to our perfect distribution, pretty much in this case, I have to say, whether we have no noise for finding the controllers or some higher noises, there are some levels where it doesn't perform so well, but these controllers were found at the noise level 0 or 0.1. On this, then we order the controllers along the x-axis, along their fidelity without noise, and the y-axis shows their rim from the color plot according to the level of noise that we apply to the system. So here, even controllers found at 0 noise with PPO remain robust up to 0.1 sigma for the simulation here, I have to say, on the perturbed system, which this was a surprising result. In particular, okay, at some noise levels, it doesn't work so well. So there is a preference for specific noise levels that we're seeing. And if you compare it with LBFGS, these controllers are a lot less robust. What is difficult to see from these plots here, though, is that the fidelity of PPO at no noise is generally lower than the fidelity that LBF tries to achieve. So higher fidelity controllers, not as robust that we get from LBFGS with PPO. We find very robust controllers on this. We'll summarize this to make a bit more sense across all of the cases. And that's this plot here, where we then said, okay, let's look at an algorithmic rim. So that's the Wasserstein distance of the Wasserstein distance. I know, but it works. So we take the rim for a particular algorithm and the values we get across, and then out of that, we get a probability distribution for the rims that a particular algorithm can achieve, and then we can compare it with the probability distribution at 0. So you want it to be at 0. That gives us sort of a summary measure of how a particular algorithm is working. Here, there's a few things in here. This is a complex plot, but effectively the color indicates the noise level at which we found the controllers. The circle says this is PPO. The triangle, that's a SNOP fit variant. That's one of these alternatives to LBFGS to work in sort of noisy functions, but it didn't work much better, more consistently, but not better, at least if you want robust controllers. And we have the green here line here with LBFGS that just has the diamond signal on it. So chains from 4, 5, 6, 7. The first part is from start to the center. The next row is from end to end, or from start to end, whatever end you want to call the start. And if we look at that, you'll see most of the time, well, LBFGS starts very low, nearly 0, very small parts. And then, well, as we increase the noise to the system, overall, the controllers don't perform that well anymore. And depending, of course, sometimes a bit better, sometimes a bit well. So we find very high fidelity controllers. For some cases, not so high fidelity. They're the more difficult cases to solve on this. But generally, their fidelity drops as the noise is increasing in the system. If you look instead at the PPO, well, a lot of them, also they start noise low, but the fidelity is actually dropping. But you see some, the yellow one here, which would be the 0.02 noise level, or here the pink one, which would be 0.04, and a few others. So at some noise levels, the controllers overall, this is a summary of all the controllers that these algorithms have found, remain fairly low. There's of course one that in all of them that is particularly good, but generally that gives us some confidence that PPO actually particularly finds the robust controllers where LBFGS is completely failing. And also the particular optimization, sort of the snub fit, you might see some blue triangle lines in here. They're not really any different. They lie on top of all each other. They all do the same thing, but they're not much not much better than really LBFGS. So, okay, if I'm looking at the time, I skipped over the magnetic resonance spectroscopy. If you want to know a bit more, I can explain that and maybe in the questions. But overall, I'd say, yes, robust quantum control is needed to build practical quantum devices if you want to be able to mass manufacture them in some sense and not just have a physics experiment. There's some progress that we've made, but really we do not have a theory of robust quantum control. We've seen some of the things that we had originally. And in particular, we do not know what the fundamental limitations are in quantum control. And there's some indications, but we see some violations to the classical theory, so there are some problems with this. These direct feedback quantum devices promise high robustness from what we've seen from the energy landscape control schemes. And we have this optimal robustness at the optimal fidelity performance, which exactly contradicts the robust theory. And a bit surprisingly, what we've seen then with the reinforcement learning approach, particularly with PPO, we find high fidelity fairly robust controllers, where LBFGS usually finds high fidelity controllers, but often they are not robust. The picture is not that consistent. I can't show you all the images, so sometimes it works better than in other times. So there's also more work, of course, we'll have to do on this. And particularly also certain noise levels seem to help to find good controllers. So that's a little bit along the lines that at certain noise levels, the landscape seems to be nicely smoothed out that you can effectively go across them about all the sort of traps that you would otherwise have in your optimizations. And that rim, or the algorithmic rim, helps us also to quantify the high fidelity robustness, not yet really to optimize for it. But if PPO stays that good, then of course this might work well. I have to add to that, these are all simulations. There is no experiment yet. That's kind of the next step that we actually need to verify. Does it actually work in an actual experiment with these energy landscape control schemes? That is, of course, more work. Okay, thank you.